Hello everybody, I am Anandavalli. You are watching Guidancee Education channel. Welcome to this new video from this channel. We are continuing class 11 chemistry, classification and periodicity of property. Periodic properties part 11. We will discuss factors deciding electron gain enthalpy and then pass on to trend of electron gain enthalpy in the periodic table with explanation for a few exceptional elements. Before we start the topic, please subscribe my channel and support. Thank you. Why should we know the factors affecting electron gain enthalpy? It is because if you know the factors affecting or deciding electron gain enthalpy, you can easily understand the trend of electron gain enthalpy in the periodic table and also explain why some elements do not fit into the general trend. So watch the video completely without skipping. Three important factors decide the electron gain enthalpy. They act in combination. That is, one single factor alone does not decide. All these three factors act together and decide the electron gain enthalpy of an element. The first one is atomic size. Electron gain enthalpy decreases with increase in size of the atom. That is, the value becomes less negative. So in terms of electron affinity, the electron affinity decreases. The negative sign of electron gain enthalpy suggests that it is an exothermic process. So as the size of the atom increases, the corresponding atom is able to expel or give out less amount of energy. This is because when the size of the atom increases, the distance of the outermost shell into which the electron has to be accepted becomes greater from the nucleus. So the attraction of the nucleus on the electron, that is incoming electron, becomes less. Nuclear attraction decides the ability of the atom to accept the incoming electron, that is its reactivity. So with increase in atomic size, the electron gain enthalpy becomes less negative. That means with decrease in size, the electron gain enthalpy becomes more negative. So when we consider atomic size as a factor individually, electron gain enthalpy becomes less negative as we go down the group and more negative as we move from left to right. But we have to consider other factors as well. Second factor, nuclear charge. When the atomic number increases, the nuclear charge increases across the period and down the group. Across the period, the atomic size decreases. Down the group, the atomic size increases. Electron gain enthalpy becomes more negative when the nuclear charge increases. Across the period, the atomic size decreases and nuclear charge increases. So, the combined effect will be greater negative value of electron gain enthalpy across the period. But what happens down the group? Down the group, the size is increasing. So, the electron gain enthalpy tends to take a less negative value. But the nuclear charge increases down the group. So, the value tends to take a more negative value. So, they seem to contradict each other. We have also to consider the third important factor. What is the reason for the increase or more negative value of electron gain enthalpy with increase in nuclear charge? The effective nuclear attraction increases with increase in nuclear charge. So, the incoming electron can be easily taken into the outermost shell. The third important feature is electron configuration. The electron gain enthalpy will be very large positive value if the valence shell electron configuration is half filled or completely filled. Positive value of electron gain enthalpy suggests that it is difficult to add an electron to the already existing number of electrons in the valence shell. The process, which is otherwise exothermic, now becomes endothermic. Large amount of energy has to be supplied. The atom has to absorb energy in order to accept an electron. The reason for this is that half-filled or completely filled electron configuration for the outermost shell gives extra stability for the atom. So the electron gain enthalpy of a particular element in the periodic table will be decided by all these three factors simultaneously. Or the trend of electron gain enthalpy in the periodic table depends upon the combined effect of all these three factors. Now we will proceed to see the trend of electron gain enthalpy in the periodic table. I will also explain why a few elements are exceptional to the general trend. Now let us understand the trend of electron gain enthalpy in the periodic table. In order to support my explanation, I have given a small portion of the periodic table here. Please go through the electron gain enthalpy of the first group elements. You can notice here, down the first group elements, the electron gain enthalpy becomes less negative progressively. That is, the addition of electron becomes more difficult down the group. All the elements in the first group have negative electron gain enthalpy. In spite of increase in nuclear charge due to the large size of the atom, the size of the atom overweighs the nuclear charge. So the electron gain enthalpy of the first group elements goes on decreasing. This is in perfect agreement with the increase in electropositivity down the first group. In the second group, beryllium and magnesium has positive electron gain enthalpy. We have already discussed the factors influencing or deciding electron gain enthalpy, and we have seen there atoms having more stable electron configuration like half-filled and fully filled valence shell electron configuration. The electron gain enthalpy will be positive. Beryllium belongs to the second period and magnesium belongs to the third period. The electron configuration of beryllium Z is equal to 4 is 1s2, 2s2, and for magnesium atomic number 12 electron configuration is 1s2, 2s2, 2p6 and 3s2. The outermost shell in beryllium and the outermost shell in magnesium are fully filled. Therefore, it becomes difficult to add an electron. Energy has to be supplied from outside. Therefore, for beryllium and magnesium, the electron gain enthalpy takes up a positive value. Across the group, as the atomic size decreases, we expect the electron gain enthalpy to become more negative with reference to the previous element. But in the case of beryllium and magnesium, the values are positive. Their exceptional behavior is due to the stability of their electron structure. Magnesium requires more energy than beryllium. It is because magnesium atom is bigger than beryllium, so the electrons are little far away from the nucleus. Leaving the transition elements, when we come to the 13th group, we can see all the elements in the 13th group have negative electron gain enthalpy. But on close examination, you can find that the trend is not as regular as in the case of first group elements. Up to indium, the electron gain enthalpy progressively becomes less negative. But for thallium, it is more negative value. So thallium shows exceptional behavior. Indium belongs to the fifth period and it is a D block element. whereas thallium belongs to 6th period and it is a F block element. Thallium, atomic number 81, electron configuration, xenon 54, 4F14, 5D10, 6S2 and 6P1. Indium, atomic number 49, electron configuration, krypton 36, 4D10, 5S2 and 5P1. Shielding effect offered by F subshell is much less than that of D subshell. So in thallium, when an additional electron is added, the F subshell offers less shielding effect. So the nuclear attraction on the incoming electron will be more. So it readily accepts the electron. When compared with that of indium, where the D subshell offers more shielding effect and it is more difficult to accept the incoming electron. Now the 14th group, the electron gain enthalpy decreases progressively up to germanium, agreeing with the general trend of electron gain enthalpy in a particular group. But the next element down the group, namely tin, has more negative electron gain enthalpy, and for lead it decreases. Germanium belongs to 4th period, atomic number is 32 and the electron configuration is argon 18, 3D10, 4S2 and 4P2. For tin, the atomic number is 50 and the electron configuration is krypton 36, 4D10, 5S2 and 5P2. Both of them belong to the D block. For tin, the electron gain enthalpy is more negative because the nuclear charge, as you can understand it from its atomic number, is much greater than that of germanium. When nuclear charge increases, the electron gain enthalpy becomes more negative. Now, when we consider the atomic size, tin atom is bigger than germanium atom, but the nuclear charge overweighs the atomic size. So the electron gain enthalpy of tin is more negative than that of germanium. We will consider nitrogen and phosphorus in the 15th group. Nitrogen belongs to the 2nd period and phosphorus belongs to the 3rd period. Nitrogen has positive value of electron gain enthalpy, whereas phosphorus has negative value. So in order to add electron to nitrogen atom, we have to supply energy. It is an endothermic process, whereas for phosphorus, it is an exothermic process. Nitrogen, atomic number 7, electron configuration 1s2, 2s2 and 2p3. It has no D subshell. The atomic size of nitrogen is comparatively very small with reference to phosphorus. 2p subshell, which is the valence shell for nitrogen, is half filled. So it is stable. Phosphorus, atomic number 15, electron configuration neon 10, 3s2, 3p3, neon 10. For phosphorus also, the outermost shell is half filled. From electron distribution, we find that both are stable. But for phosphorus, the electron gain enthalpy is negative and for nitrogen it is positive. Nitrogen is a smaller atom, but in spite of that, the nuclear charge of phosphorus is much greater. So it can easily attract the incoming electron into it. 16th group, oxygen and sulfur. Electron gain enthalpy of sulfur is more negative than that of oxygen. Here also, the nuclear charge of sulfur is much more than that of oxygen. Atomic number of oxygen is 8, whereas the atomic number of sulfur is 16. So adding electron to sulfur is easier than adding electron to oxygen. Let us take up group 17, that is halogens. You can note the electron gain enthalpy of chlorine is more negative than that of fluorine. Fluorine belongs to the second period and chlorine belongs to third period. Due to absence of d orbitals, the second period atoms are in general very small. For the rest of the elements in the group, the electron gain enthalpy becomes progressively less negative. So the electron gain enthalpy of chlorine is more negative because of its greater nuclear charge. For the rest of the elements in the group, the increased size of the atom outweighs the increased nuclear charge. Therefore, the electron gain enthalpy becomes less negative. Coming to the 18th group, all the elements have positive values of electron gain enthalpy, which suggests that it has a stable structure. The 18th group elements, which are otherwise called inert gases or noble gas, are very less reactive because the outermost shell has the octet structure of electrons. It's supposed to be a stable structure. So energy has to be supplied in order to make them capable of taking in electrons. We have not considered all the elements in the periodic table, but with the elements that we have considered, we can easily understand that down the group or across the period, the electron gain enthalpy does not follow a regular pattern. Across the period, say for example, the second and third period, you find that the values range from less negative to more negative through positive values for a few elements to more positive values for the 18th group elements. Questions are normally asked for those exceptional elements which do not fit into the general trend. So what is the general trend of electron gain enthalpy in the whole periodic table? The answer will be the electron gain enthalpy does not show any regularity either in the period or in group. There are a number of exceptions. Hope this video was of great use to you. If you think it is useful, do like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now, and also press the bell button and all button for notification of more videos like this. Thank you very much for your support. We will meet in the next video with another important topic like this. Till then, bye. Take care.